Professor Patel. I am going to go ahead and try to present this precalculus, exponential, and logarithmic functions presentation. So let's go ahead and get started. Are like super fast growing or super fast shrinking numbers. Think of a snowball rolling down a hill, getting bigger and bigger, or think about the stock market going downhill very fast and the value of the stock is getting smaller and smaller. Logarithmic functions are their opposites. They help us undo exponentials. It's like asking, how many times do I need to multiply to get this big number? These two are best friends because they're inverse function. One builds up, the other takes apart. Today's plan. We're going to learn what these functions are, how they look on graphs, and how they show up in real life, like in music or science. This is going to be on slides 3 through 6. The definition of exponential and logarithmic functions are as followed. An exponential and a logarithmic function are two different types of functions. An exponential function is the type of function that has the form of f of x is equal to a to the power of x. A is the constant base. X is your exponent, which makes it an exponential function. If you think of the name, an easy way to remember exponential function is exponent, shul, exponential. You know that no matter what, this equation is going to have an exponent in it. A logarithmic function is the type of function that has the form of f of x is equal to log subscript a times a to the power of x that equals x. A will always be greater than 0. That will never change. The logarithmic and exponential functions are inverse functions of each other. Exponential functions raise a certain base to a power, while the logarithmic functions tends to try to figure out what the exponent the base needs to be raised to. In this presentation, we are going to go over what logarithmic and exponential functions are. We're going to go over the key properties of exponential and logarithmic functions. We will plot graphs of exponential and logarithmic functions. And finally, we will go over some real-life examples of these types of functions. Let's go ahead and get started with some practice questions. An example of an exponential function is as follows. You put $1,000 in a bank account. Your account is going to earn 7% interest monthly. How much money will you have in your account after 10 years? To solve this, we will use the following equation. 1,000 times 1 plus 0.07 to the power of 10. The 1,000 is the $1,000 you invested in the bank. The 1 plus 0.07 is how much you will make per year. And the 10 is how long it will be invested. Our answer comes up to $1,967.15 after it is distributed and solved, but I would like to go ahead and put this equation into Desmos just so we can go ahead and check our work twice. As you see, I have put in the equation here, and the answer is $1,967.15. Here's the next question. We're going to go ahead and do a simple logarithmic function equation. You put $1,000 in your bank account like last time. Your account earns 7% interest monthly. How long will it take to double your money? As you see, logarithmic and exponential functions are inverses because the exponential function was trying to figure out how much you would make in 10 years, but this one wants to know how long is it going to take to double your money. As you see, the logarithmic is trying to figure out what is the equation to the power of raised to. So our equation that we use is 1,000 times 1 plus 0.07 to the power of t is equal to 2,000. The 1,000, of course, is how much you invested. The 1 plus 0.07 is how much you will make in a year. The t is how long it's going to take to be able to make $2,000, and the 2,000 is how much we would like to make. To solve this problem, we'll use these steps. Go ahead and write this out. 1000 times 1 plus 0.07 to the power of t is equal to 2000. Then we know that we have to divide both sides by 1000 because we need to get our 1 plus 0.07 to the power of t on its own. So after we have divided both sides by 1000, we end up with 1 plus 0.07 to the power of t, which is equal to 2. Then we can go ahead and add the 1 plus 0.07, which is equal to 1 plus 0.07, which is equal to 1.07 to the power of t, which is equal to 2. Then we can use this logarithmic equation. Log subscript 1.07 times 2 is equal to 10.24. This is our answer, but I would like to go ahead and also put this into Desmos and be able to check it out and make sure that the work is correct. So let's go ahead and scroll down and find our log and our subscript. Log 1.07 times 2 is equal to 10.24. So that is how I got my answer of 10.24 years in order to double your money. This is how long it will take. On to definitions and key properties. These will be on slides 8 through 10. Is an exponential function. This is more of a mathematical definition. An exponential function is written as f of x is equal to ab to the power of x, where a is a non-zero constant that scales the function. B is a positive base, not equal to 1. It's always greater than that. And x is the variable in your exponent. This form describes rapid growth or decay depending on your base. Some properties of an exponential function. We know that your domain is all real numbers. Your range is positive. A is greater than 0. Your asymptote is at y is equal to 0. Your growth always increases fast, your decay approaches 0, and it always crosses the y-axis at 0, a. Most likely it will cross your y-axis at 0, 1, or that is the most common. As you see over here on this side, this is the graph of f of x is equal to 2 to the power of x. We will go ahead and graph this just to go ahead and see the extent of it. F of x is equal to, let's say, 3 to the power of x. As you see right here, it is crossing your y-axis at 0 and a. A in this case is 1. And we also see that from here, there are certain points that it does intersect on. We see x could be anything. 3 to the power of 1 is 3. Scroll in just a little bit. 3 to the power of 1 is 3. So we see that it intersects on 1, 3. 3 to the power of 2 is 9. So we see that it will intersect right here. Right about this point. Let's just say 2, 9 is right there. And we'll do one more. 3 to the power of 3 is equal to 27. So it will intersect on point 3, 27. And let's go ahead and scroll up to this. And there's your point there. 327. And as you see, this could just keep going on forever, but it will not. We are not going to keep doing this. So what is a logarithmic function? This is also a more mathematical term. A logarithmic function is written as f of x is equal to log subscript b times x. B is a positive base. It's not 1. X is a positive input. It answers the question, to what power must b be raised to get x? There are different rules for logarithms. There's the product rule, which is log subscript b times xy is equal to log subscript b times x plus log subscript b times y. There's your quotient rule. Log subscript b times x divided by y is equal to log subscript b times x minus log subscript b times y. Then there's your power rule. Log subscript b times x to the power of k is equal to k. Here's an example. Log subscript 2 times 8 times 4 is equal to log subscript 2 times 8 plus log subscript 2 times 4, which is equal to 3 plus 2, which is equal to 5. Our domain on a logarithmic function graph is always x is greater than 0. Our range can be in all numbers, and our asymptote is at x is equal to 0. This will always cross your x-axis at 1, 0. It will grow slowly, and it undoes exponential functions. As you see here on this graph right here, this is a exponential function, y equals a times a to the power of x, and this is a logarithmic function, y is equal to log subscript a times x. These both mirror each other, and that is how they are inverse functions. So let's go ahead and try and see what we can get to mirror each other. We will do f of x is equal to 4 to the power of x. Okay, here's your piece. It intersects on the y-axis at 0, 1. And now we are going to do f of x is equal to log 4 times x. And this one will always intersect at 1, 0. As you see, both of these are, this one right here, the one that intersects on the y-axis at 0, 1, is a exponential function. We will go ahead and then the one that intersects on the x-axis at 1, 0 is a logarithmic function. We'll do one more mirroring one. Let's just change it to 45 to the power of x. Of course, it already intersects on our y-axis at 0, 1. And then, as you also see here, it intersects on our x-axis at 1, 0. So this is how you can see the mirroring between the two different types of functions. So in summary, what are exponential and logarithmic functions? An exponential function is a super fast growing or decaying function. It's like a snowball rolling downhill. A logarithmic is the reverse of exponentials, undoing the powers. They are inverse functions. For example, f of x is equal to 2e to the power of x plus 1. That shifts the graph of f of x is equal to 2e to the power of x left by 1 unit. The horizontal asymptote remains at y equals 0, but the graph will move left. Next, I'd like to move on to some more graphical representations. This will be on slide 12. The graph of an exponential function starts at a point on the y-axis. It rises sharply to the right and flattens towards a horizontal asymptote, as we have seen from our graph of f of x is equal to 4 to the power of x, or f of x is equal to 45 to the power of x. It will accept any input with positive outputs, while the logarithmic graph crosses the x-axis, rises slowly to the right, and drops towards a vertical asymptote, taking only the positive inputs with variable outputs, and they'll mirror each other across a diagonal line. As you can see in this image over here, an exponential function is touching right here on the y-axis, and it is rising sharply to the right. And as you see here, the logarithmic function has a point right here on the x-axis, which is, I cannot see what it is at the moment. It looks like 0, 0. And it rises slowly to the right, and then it is dropping towards the vertical asymptote. As you can see, the downward shift right here, it goes up or it can go down. Shifting your exponential graph up or right will move it. Reflecting it, as you see right here, the reflection, that will flip it downward. And stretching it makes it steeper. While the same transformations on the logarithmic graph adjust its position, flip it, or increase its slope, scaling an environmental graph taller or speeding its growth changes its rise, and shifting a logarithmic graph right or down moves its asymptote or lowers it, showing how these adjustments shape their behavior. Let's go ahead and move on to some real-world examples. This is going to be on slide 14. Here's a real-world example of exponential growth. Bacteria in a petri dish often grow exponentially when resources are plentiful. So this does not mean they always grow. This means when the conditions are favorable, they will continue to multiply. So suppose your culture starts with 50 bacteria, and it doubles every hour. So the first hour you will have 50, the second hour you will have 100, 150, 200, and so on. The model is p times t is equal to p subscript 0 times 2 to the power of t, where p subscript 0 is equal to 50 because 0 is the same as 1 hour. T is time in hours. So after 3 hours, the population is p times 3 is equal to 50 times 2 to the third, which is 50 times 8, which is equal to 400. As you see, 2 to the third, 2 times 2 is 4, times 2 is 8. 50 times 8 is 400. This helps predict the bacterial spread, which is useful in food safety to prevent contamination. If you think about the exponential function right here, this could actually save someone's life. If the bacteria multiplies too rapidly, or there isn't enough bacteria in, let's just say, something like milk, if someone gets sick from someone not knowing about the exponential growth of the bacteria, things are going to go really bad. Someone could sue the milk company, or someone could die and lose their life. This is why exponential functions are very useful in the real world. Let's go ahead and move on to a logarithmic growth equation. So for the logarithmic scale, we are going to talk about earthquake magnitude. Earthquake strength is measured on the Richter scale. A logarithmic model given by m is equal to log subscript 10 times a. A is your amplitude of the seismic waves. If an earthquake has an amplitude 1,000 times the reference level, then m is equal to log subscript 10 times 1,000, which is equal to 3. This scale simplifies comparing earthquake strengths, aiding in disaster preparedness and building design. I would like to just talk about these earthquakes for just a second. If you think about the Richter scale, actually I have an image of this. Here we go. The Richter scale is very, very useful because if you were thinking about an earthquake, you see from here that it goes from level 1 to level 9, and you see the kilograms that are equivalent to that amount of TNT. The Richter scale is very helpful because it helps in disaster relief, because what I'm trying to say here is that the Richter scale, this will help aid in disaster relief because if you know what the earthquake magnitude is, it can help you improve the building design, it can help you improve the foundations, the structure, the walls, and everything you need to know if you have an estimate of an earthquake, or if you live in an earthquake prone area. Then you realize, okay, this area could be hit by a level 7 magnitude earthquake, so you know that you need to make everything in your building stronger. You also know that because of the Richter scale and the logarithmic growth, that when you have a predicted level 7 earthquake on the Richter scale, that you know that, hey, I'm going to have to get even more prepared for this than I was for, let's just say, a level 2 on the Richter scale. So why are these equations important? Exponential models help track the rapid growth, ensuring timely interventions in health and safety. As I stated before, this could save someone's life in the health and medical field just because of bacteria growing too rapidly or not growing enough. And it promotes safety, because if people are not losing their lives from no one knowing what the exponential growth of the bacteria is, that's how it helps. The logarithmic scales make large differences manageable. They improve analysis in fields like seismology. These tools simplify understanding and solving practical challenges. Excuse me. Sorry. Let's go over some key points. Exponential functions defined as f of x is equal to a times b to the power of x. They model rapid growth or decay with a domain of all numbers and a positive range, while logarithmic functions, f of x is equal to log subscript b times x, are their inverses. They take positive inputs, they produce any output, they grow slowly, and graphically, exponentials rise or fall sharply with a horizontal asymptote, and logarithms increase gradually with a vertical asymptote. They both shift, flip, or stretch under transformations, like moving up or scaling. In real life, exponential growth tracks bacteria doubling, aiding in food safety, and logarithmic scales measure earthquake strength, helping with disaster planning, showing how these equations simplify and solve practical problems. As well as going over these key points, I would like to go back in the slides and slow down just a little bit and do some example questions and try to explain this just a little bit more. First, I would like to go back up to an exponential function. We know that an exponential function is written as f of x is equal to a times b to the power of x. A is, of course, our non-zero constant that scales the function. B is our positive base that's not equal to 1. Because if you just have, let's just say, A is 2, B is 3, and x is 1, 2 times 3 is 6. 6 to the power of 1 is just 6. You can't use that. That just does not work with the graph. So let's actually graph that and see why it doesn't work. F of x is equal to 2 times 3 to the power of 1. As you see here, it's a straight line. This is not categorized in exponential or logarithmic. This would not be categorized in an exponential function because, as you see, it does not intersect on the y-axis at 0, 1. It also does not start at the point, go up, and start going up towards the right. So this is an example of an actual exponential function. F of x is equal to 23 to the power of x. As you see, this intersects on point 0, 1, which I will go ahead and label. It is also on the x-axis right here, and it's coming up, and then it intersects on the y-axis, and it just keeps going. And of course, you see the next point that it would touch after 123 is equal to 529, which I will go ahead and let's see if we can get up there. Just labeled that. So let's see. There is the next point. And as we know, 23 to the third, that is 12,167. So the next point it would intersect on would be 3 and 12,167, which we can also see, which is right here. Let's do one more example of an actual exponential function. F of x is equal to, let's just say, 5 to the power of x. Well, let's do 10 to the power of x. Scroll back in here. As you see, the first point is on 110 in just a moment, but it is also intersecting first on 01, which is labeled in purple. And as you see here, 110 is right here. Then it will intersect on 220. Somehow I've made a mistake here. That's not correct. 110. Oh, excuse me, that's why. I'm so sorry. 10 to the power of 2 is 100. So it would intersect on 100 instead, not 220, because 10 times 2 is 20 and 10 times 10 is not. And that is your point 100 right there. I would just like to scroll back in just so you can see this graph just a little bit more. This is an exponential function example. Okay, let's go ahead and move on to the logarithmic functions. We know that, of course, the logarithmic function is f of x is equal to log subscript b times x. B is the positive base that's not 1. X is a positive input, and it always answers the question, to what power must b be raised to get x? We also know that exponential and logarithmic functions actually, they will mirror each other on the graphs. We remember our product rule. Log subscript b times xy is equal to log subscript bx plus log subscript b times y. Let's go ahead and do a practice equation here. Let us say, let me get me a piece of paper right here. Let's say log subscript 4 times 3 plus log subscript 4 times 7. This is our equation right here. We know that they are going to be added, and the final answer will be log subscript 4 times 21, because 3 times 7 is 21, and of course you still have your log subscript 4. Let's go ahead and do the quotient rule. We'll use different numbers than last time. Log subscript 2 times 6 minus log subscript 2 times 2 is equal to log subscript 2 times 3. That is an example of the quotient rule. The power rule. Let's go ahead and do this one. Log subscript, let's say 7 times 3 to the 4 is equal to 4. And I want to make sure and recheck my work that this equation, this example that I have put down here is actually accurate. So I see that I have log subscript 2 times 8 plus log subscript 2 times 4. We know that it is going to be equal to log subscript 2 times 32, which I actually messed up my answer here. Excuse me for that. It is equal to log subscript 2 times 32. Excuse me, I'm sorry about messing that up. So we know that our domain is going to be x is greater than 0. We see that our range is all of our numbers. Our asymptote is going to be at x is equal to 0. And of course, a logarithmic function crosses the x-axis at 1, 0. It will grow slowly and it undoes exponential functions. We will go ahead and plot an example on Desmos. So let me write this down. We know that we are going to be crossing at 1, 0 on the x-axis. It's going to go up slowly, and it is going to undo the exponential. So let's go ahead and move on over to Desmos. And we can actually make up an additional practice problem in just one moment. An example of a logarithmic function will be right here. Let's do log subscript 5 times 3. Oh, wait a minute. I did not do the right one. That's why. Log subscript 5 times x. Excuse me. You always have to have that x variable in here in order to actually have a logarithmic expression. So, as you see from our notes just a moment ago, does it cross, I probably shouldn't have put that yet, does it cross the x-axis at 1, 0? Yes, it does. Here's our x-axis. Here's 1, 0. So, is this going to grow slowly? Well, let's see. As you see, it is a very gradual increase. So we aren't getting very far, even as we're out to already 100, and we aren't even up to 5 yet. So as you keep going, it just is still growing slowly, extremely slowly. And I also would like to see if this one will undo the exponential, and I want to see if the exponential goes on 0.01 for the y-axis. So the inverse equation of log subscript 5 times x is actually f of x is equal to 5 to the power of x. As we see here, does it intersect on the y-axis at 0, 1? Well, I don't know. Let's see. Yes, it does. Here's our y-axis. Here is our point that it's intersecting at. Does this grow rapidly? Compared to our logarithmic function, this grows very fast. Look at the line continuously going up, and it's getting farther and farther and farther out. And by the time that you are at 100, you are already growing you're still growing very rapidly. And we see that this equation does undo the exponential function. And we also see here that this is an inverse function because they are mirroring each other. Let's do another example. Let's go ahead and do log, log 45 times x. Does this intersect on 1, 0? Yes, it does. So that is one key indicator that this is a logarithmic function. Does it grow very slowly? Yes, it does. And is it going to undo the exponential? I don't know. Let's go ahead and graph the exponential that is the inverse. So first, we see that they are mirrored equations. So that is a very good indicator that they are inverse and that they are going to undo one another. But besides from that point, does the exponential function that is so-called the inverse of this intersect on the y-axis at 0, 1? Yes, it does. This is another example of how these two are inverse functions, how they are able to undo each other, and where they both intersect on the x and y axis. Okay, here we go. So we know that just from even the graphs that we have just finished, that the exponentials grow super fast or they have super fast growth or decay. It really just depends on what the equation is. We know that the logarithmic is, of course, the reverse of the exponential. It undoes what the exponential function does. So, of course, we have our example, f of x is equal to 2e to the power of x plus 1. It'll shift our graph. But let's go ahead and just graph this. F of x is equal to 2e to the power of x plus 1. This is an exponential function. Does it intersect on the y-axis? Yes, it does. Our exact point is at 0 and 5.43656, which of course, as I stated earlier, the coordinate will always be 0 and a. Most likely, it will be 0, 1, but it really does not have a certain limit to what it could be. I mean, the point could literally be anything. So we see that this graph shifts the graph of f of x is equal to 2e to the power of x. F of x is equal to 2e to the power of x. And we see this graph, which they are both on the same coordinates right here, which is -6, 0. And we see that it is going to shift the exponential function of 2e to the power of x plus 1 to the right by 2 units. Excuse me, left by 1 unit. The horizontal asymptote, of course, is at y equals 0, but the graph will move left. Let's go ahead and do another example to see how far the graph actually can move over, how many units, for example, what? Let's do f of x is equal to, let's say 5e to the power of x. Let me go ahead and delete that one. And then we will have f of x is equal to 5e to the power of x plus 4. As you see, this will transition our graph over 4 units. And this is exactly like the previous equation. Okay, let's go ahead and try one more example here. Let's say f of x is equal to 45 to the power 45e to the power of x. And then let's say this one is f of x is equal to 45e to the power of x plus 7. As you see, our graph has moved 7 spots over, and this is also an exponential function. This graph, we are talking just a tad bit more about graphical representations. This is going over the reflections, the stretching, the upward and downward shifts, and the exponential functions, and logarithmic functions, I mean. As you see, certain conditions will make your graphs change. So if your graph shifts up or moves right, reflecting it flips it downward, stretching it makes it steeper, while the same transformation on logarithmic graph just adjusts its position, flip it, or increase to find its slope. We went over some real-world examples of exponential and logarithmic functions. Of course, we went over the bacteria in the petri dish, which I would like to do another quick example just to see if we can get another solution. So let's just say we have our model p times t is equal to p subscript 0. Let's say that we have 150 bacteria to start out with in our culture. Let's say it triples every hour. So we will go ahead and use our equation. P time, and I want to figure out how long it'll be in 4 hours. So we see P times 4 is equal to P times 4 is equal to P times 4 equal to 150 times 3 to the power of 4. 3 to the power of 4 is 3 times 3 is 9 times 3 is 27. 27 times 3 is 81. So 150 times 81 will be 12,150. So by the time 4 hours has passed, we will now have 12,150 bacteria in our petri dish. The last real-world example that we talked about was the Richter scale and how it helps in seismology. So let's go ahead and try a quick example here. We see that we have m is equal to log subscript 10 times a. A is your amplitude. But if our amplitude is 1,000 times our reference level, we of course have log subscript 10 times 1,000 is equal to 3. But let's check the work. Log subscript 10 times 1,000 is equal to 3. Okay. The last slide I'd like to go over is this slide. I'd like to tell you, Professor Patel, thank you for watching my presentation on the exponential and logarithmic functions. In this presentation, we covered definitions, properties, graphs, and real-world uses like bacterial growth and earthquake scales. I do hope you find this presentation insightful. I would like to say to you, I really appreciate you giving me this opportunity. I appreciate being able to learn and grow and get more out of this class than I actually expected. In this class, I feel like I have learned more than I have learned in college algebra or high school courses, because I have taken advanced precalculus in high school, and this class has just given me more of a in-depth explanation of it, which I really enjoyed because I am a math person. So overall, I'd like to say thank you for giving me this opportunity. Thank you for letting me be able to do these extra projects, and thank you for being an excellent teacher this semester. I hope you have an absolutely wonderful rest of your year, and I hope we get to talk in the near future. Have a wonderful day.